Modeling of magnetic hysteresis of core iron of a three-phase transformer.
A transformer is defined as a passive electrical device that transfers electrical energy from one circuit to another through the process of electromagnetic induction. It is most commonly used to step up or step down voltage levels between circuit. Transformers are one of those important pieces of equipment that make modern life possible, as they provide a critical power conversion function. They step up or step down AC voltage or current to useful levels, which then can be converted to DC and used to power your favorite electronics. If you want to plug anything into the wall and receive grid power, there are some important requirements you'll need to satisfy, one of which relates to hysteresis in a transformer. Unfortunately, with magnetic hysteresis comes hysteresis loss in a transformer. Every transformer exhibits some hysteresis loss as the input current oscillates back and forth, and these losses manifest as minor distortion and reduced efficiency in the output power. Incorporating magnetic characteristics of the core is important when representing the real-world transformer in a simulation environment. Therefore, we have developed a mathematical magnetic characteristic model to incorporate the magnetic hysteresis effect to the transformer models that are established at present. Major limitations identified in existing transformer hysteresis models are: most commonly used Giles-Atherton model requires 5 core-specific input parameters related to magnetic properties of the core material. These estimations involves complex approaches. Also, physical asymmetries along magnetic paths are not considered in many models. We have developed the magnetizing characteristics model through a test-supported mathematical approach by extracting the magnetic characteristics of the 3 limbs separately. When we give a sinusoidal voltage input to the magnetizing characteristic model, it outputs a magnetizing characteristic relationship curve in that distinct voltage level. Magnetic characteristic at rated voltage is an input parameter of the model. The shown characteristic parameters are automatically estimated related to the operating voltage level, based on the mathematical equations and functions embedded in the system. Magnetic characteristics of transformer core was extracted using 2 limb-wise tests. To establish a flux path only in the outer core path, 2 in phase, inverted currents are given and adjusted to phase A and C of the transformer primary side, such that induced voltage in the phase B of the secondary side will be 0. In test 2, 2 in phase currents are given and adjusted such that induced voltage in the limb A secondary side is 0. Waveforms of both currents and induced voltage of phase B secondary side are recorded. Recreation of the magnetic characteristic parent curve was conducted by generating the ascending and descending curve paths of BH loop from the mean double exponential curve, using the saturation point and the coercivity point. The options available are categorized as the availability of magnetizing characteristic data for different scenarios. Option 1 is, in case of magnetic characteristics of multiple voltage levels are available as data. Option 2 is developed for more practical occasions, such as magnetic characteristics for rated voltage is only available. Now we have reached the most important section of this video. That is, how to implement the developed model in real-world applications, and the uniqueness of our model, compared to the contemporary transformer models. First, we will pay our attention on how this hysteresis model works. First, we have to disconnect the load from the 3-phase transformer, and conduct the no-load test. Then, extract the voltage and current data at the rated excitation. Using those data, the BH curve at rated excitation is plotted. Then, the characteristic parameters in the model are changed, in a way that the model BH curve is closely matched with obtained magnetizing characteristic curve. Finally, the recreated parent magnetic characteristic curve is used as an internal input to the model. Then, the magnetic characteristic curve, for any distinct voltage level can be constructed using the desired options. We can use this test-based limb-wise model on magnetic hysteresis in many research-level applications. Also, this is a simple implementation compared to the more complex contemporary models that are frequently used. Using our hysteresis model and periodically extracted magnetizing characteristic data, we can investigate the changes occurred in the core of the transformer, due to aging and environmental factors. At the same time, we can use this model to get a sound knowledge and compare and contrast the magnetic properties of transformer core materials. With the results of those comparisons, the manufacturers can develop their transformers with preferred raw materials that have the best magnetizing properties. This video is based on the final year undergraduate project, named as Modeling of 3-Phase Transformer Incorporating the Magnetic Hysteresis of Core Iron, conducted by a group of undergraduates of Department of Electrical Engineering at University of Moratuwa. Thank you.